Hello, in today's video, we're going to take a deep dive into functions and how you can use them in the Go language. Now we've been talking about functions throughout this entire video series, but we've never really taken the time to focus on them because there's a lot of groundwork that we've had to go through building up to the point where we can understand what a function is and how we can use those in our applications. So in today's video, like all of our videos in this series, I'm going to break the discussion down into multiple parts. We'll start by talking about the basic syntax of a function. Then we'll talk about the parameters that you can pass into a function to influence how it works. Then we'll talk about the return values that you can get back out of a function. We'll talk about something called an anonymous function. We'll talk about how functions in the Go language are first-class citizens and can be passed around in your application like any other variable. And then we'll wrap up our discussion by talking about a special kind of function called a method. Okay, so let's get started by learning the basic syntax of a function. To start our discussion of functions, we don't have to go any farther than the basic application that the Go playground gives us. So as soon as you come into the playground, you're presented with this very simple application, and right here we have our first function. Now the way that a Go application is structured is you always have to have an entry point in the application. And the entry point of a Go application is always in package main, and within that main package you have to have a function called main that takes no parameters and returns no values. So we can see that right here. And so when we run the application actually starts right here. And so we print out the string hello playground, and that's all that our application has to do. So every Go application starts this way, and we see here the most basic function that we can create in the Go language. So there are several major parts that we need to understand about a function. First of all, they start with the func keyword. So as you can see here, we're not going to start with function or anything else. We start with the func keyword, and that's going to describe a function that we're going to create. Then we have the name of the function that we're going to create, and this follows the same naming convention as any other variable in Go. So you're going to use Pascal case or camel case for the names of your functions, and depending on if you have an uppercase or lowercase, determines the visibility of that function. So just like with variables, an uppercase first letter is going to be published from the package so anything else can use it, and a lowercase function name is going to be kept internal to the package. Now after the name of the function, we have these matched parens here. Now we'll see as we get into parameters what these are for, but this is required syntax after the main function. So even if you don't take any parameters in your function, you have to have these matched parens. And then the actual body of the function is contained within these curly braces here. Now, there are a lot of holy wars in a lot of languages about where these curly braces should go. So some languages put them here, some languages put them down here, some languages like to indent them. There's all sorts of different conventions about where to put these curly braces. Well, in the Go language, there aren't any arguments because this is the convention that is enforced by the compiler itself. So you have to put the opening curly brace on the same line as the func keyword, and then the closing curly brace generally has to be on its own. Now there are a couple of situations where you can have that closing curly brace combined with a couple of other parens, and we'll talk about that a little bit later in this video, but generally speaking, when you're defining a function, the closing curly brace has to be on its own line. Now with functions defined like this, the execution path is static. We can't actually influence what our function's doing from the outside, because we're not passing any information into it. So if we do want to pass information into it, then we're going to provide what are called parameters into the function. So let me just drop an example that uses parameters. And you see here our main function is now calling into another function called sayMessage. And that sayMessage function takes in this parameter MSG that's of type string. So when you're defining a function that takes parameters, the parameters go between these two parentheses here, and they're described like any other variable declaration except for you don't need the var keyword. So you're going to have the name of the parameter and you're going to have the type of the parameter. So then when we want to call that function, we have to pass in the value for that parameter, and that's called an argument. So we're going to pass in the argument hello go, and then inside of our function we're printing out the message that gets passed in, and so when we run this, we see that hello go prints out as a result. Now this MSG parameter isn't special in any other way than the fact that it's passed into the function. It's treated as a local variable just like any other local variable that we might create. So if we created another variable here, and we said hello go, that's treated exactly the same way as our MSG variable. So the only difference between the two is the MSG variable can be passed in from the outside, and of course that greeting variable was created locally. Now you aren't constrained to just pass a single parameter in. You can actually pass multiple parameters in. So if I drop in this example, we can see that in action. So here I've extended the sayMessage function to take two parameters. So I've still got the message parameter that's of type string, and then I've put this comma here, and I've added another parameter, and that's going to be an index, and that's going to be of type integer here. So as you can see, we can pass as many parameters as we want. We're just going to provide a comma delimited list of those parameter names and their types. So then when we call the function, we're going to pass in one value for each one of those parameters, and they have to be in the same order that they're declared. So the first argument that we're going to be passing is the string hello go, which is going to match this MSG variable. And then we're going to pass in the I that's going to be the loop counter here, and that's going to be passed into this IDX parameter. So then in this function, we're just going to print out the value of the message, and then we're going to say what index we receive. So when we run this, we see that the message prints out 5 times, and we get the same message, but the index variable changes because we're passing in a different value every time we call the function. Now, often when you're defining a function, you're going to pass in multiple parameters of the same type. So you're going to be tempted to have syntax like this. So in this example, we've got a slightly different function. So instead of a generic say hello, we're going to have a say greeting function, and we're going to provide the greeting that we're going to have and the name of whoever it is we're going to greet. So in this case, we're passing in the string hello and the string Stacy. So when we run this, we're going to say hello to Stacy. Now, since these types are the same, the Go compiler actually provides us a little bit more syntactic sugar because this is a little bit more verbose than is strictly necessary. So instead of specifying the type every time, we can actually just specify a comma delimited list of variables and then the type at the end. And what the compiler is going to do is it's going to infer that every variable that's in that comma delimited list has the same type. So when we run this, we actually get exactly the same execution, but we just have a little bit more terse syntax. Now, so far, we've been passing parameters in as value types. If you remember from our last discussion, we were talking about pointers, and notice that I don't have any pointers in our function signatures right now. So let me drop in this example here, and then we can start playing around with the difference between passing in values and passing in pointers. So when I have this example here and I run it, we get exactly the same output that we had before, but I've got some variables that I'm using to pass in as arguments to this function. Now, what do you think is going to happen if I change the value of one of these variables inside the function? So for example, if I change the name variable to Ted, and let's go ahead and print that out just to verify that it printed. And then what do you think is going to happen if I print the same variable out again right here? So I'm passing in the name variable by value. So that means that the Go runtime is going to copy the data that's in this name variable and provide it to here. So what we would expect is when we change the value of the name variable right here, it should have an effect and we should print 10 out here. But since this is a copy of the name variable, we actually shouldn't have any effect out here. So if we run this, we see that in fact that is true. So this is a safe way to pass data into a function. You can be assured by passing by value that the data is not going to be changed when you pass it in. Now if I change this to passing in pointers by adding a pointer here, and then passing in the address of these variables right here, and then dereferencing the pointers right here, then let's see what's going to happen. Actually, I need to add another dereference right here, and now we're passing pointers to our variables around in our application. So now, instead of working with a copy of the name variable, we're working with a pointer to the name variable, and so when we run this, we actually see, looks like I missed a dereference operation right here, and now we see that we have in fact changed the variable not only in the scope of the function, but in the calling scope as well. So by passing in a pointer, we have in fact manipulated that parameter that we passed in. Now why would you want to do this? Well, there's a couple of reasons. First of all, a lot of times our functions do need to act on the parameters that are passed into them, and so passing in pointers is really the only way to do that. The other reason is passing in a pointer is often much more efficient than passing in a whole value. Because right now we're passing in simple strings, and strings aren't that large in Go, so passing in copies versus passing in pointers is pretty much going to be the same in terms of performance. However, if you're passing in a large data structure, then passing in the value of that data structure is going to cause that entire data structure to be copied every single time. So in that case, you might decide to pass in a pointer simply for a performance benefit. Now you do have to be a little careful when you're passing in pointers because of course you can't inadvertently change that value, and so you can cause some issues for yourself. Now just to remind you of something else that we talked about in the pointer discussion, if you're working with maps or slices, then you don't really have this option, because since those two types have internal pointers to their underlying data, then they're always going to act like you're passing pointers in. So just be careful when you're using those data structures, because you can inadvertently change the data in your calling function when you're manipulating them within the called function. The last thing that I want to talk about when we're working with parameters are what are called variadic parameters. So if I drop in this example here, we can see an example of a variadic parameter. So in this case, I've got a generic sum function that I'm creating here, and I'm passing in the numbers 1 through 5. Now I'm not receiving 5 variables here. Instead, I've got one variable here, and I've preceded its type with these 3 dots here. So what that's done is that's told the Go runtime to take in all of the last arguments that are passed in and wrap them up into a slice that has the name of the variable that we have here. So then inside of the sum function, we're going to print out what that values object is, just so we can see that. And then we're going to go ahead and add up all those values in there. So since it's going to act like a slice, we can use a for loop and range over those values. And then we're going to print out the result of that. So when we run this, we see that we do in fact have a slice that's printed out. The sum is 15, so we got that result printed out properly, and there's no problem at all. Now when you're using a variadic parameter, you can only have one, and it has to be the last one. So if I, for example, want to have a custom message string, I can pass that in, and then pass that in here, and then replace this, and this still works just fine. However, I couldn't, for example, put the message parameter as the last parameter, because the runtime doesn't have the ability to understand where the variadic parameters end and where additional parameters would begin. So if you're using variadic parameters, you can only have one, and they have to be at the end. Okay, now it's nice to be able to pass data into our function, because now, depending on the different data that I pass in, I can change the behavior of the function. But it's also very useful to be able to use our functions to do some work and then return a result back to the calling function. So in order to do that, we're going to use what are called return values. So if I drop in this example, we see it's basically the same as our last example, but instead of printing the message in the sum function, we're returning the result out, and then the main function is actually working with that. So there's a change we had to make in our function signature. So right here after the parameter list and before the opening curly brace, I've listed the return values type. So in this case, I'm expecting to return an integer, so I just put int right here. Inside of my function, I'm going to use the return keyword, and then I'm going to return the value of the variable that I've been building up throughout the course of the function. So in this case, I declare the result variable here, I populate it in this loop, and then I return that result back. Now up here in the main function, I can catch that return value by declaring a variable and setting it equal to the result of this function. So s is actually going to be an integer type, because that's what's returned out of this function, and then I can work with that integer. So if I run this, I get exactly the same behavior that I had before, but now the sum function is more of a pure function. It doesn't care what I do with that result, it's just going to generate the result and return it back to the caller. Now another feature that Go has that's actually pretty rare in a lot of languages is the ability to return a local variable as a pointer. So in our previous example, when we returned that result, Go actually copied that result to another variable, and that's what got assigned. But we can also do this. So if you look here, I'm returning a pointer to an integer now, and instead of returning the result, I'm returning the address of the result. And so s is now a pointer, so I've changed to a dereference operation. So if I run this, it works exactly the same way. Now, again, if you're coming from another language that uses pointers a lot and doesn't abstract away the differences between working on the stack and working on the heap, then this might freak you out a little bit. Because when we declare the result variable, it's actually declared on the execution stack of this function, which is just a special section of memory that's set aside for all of the operations that this function is going to be working with. So when this function exits, that execution stack is destroyed. That memory is freed up. And so in a lot of languages, this is not a safe operation, because now you're returning a pointer to a location in memory that just got freed. And so you've got no idea what value is going to be there. Well, in the Go language, when it recognizes that you're returning a value that's generated on the local stack, it's automatically going to promote this variable for you to be on the shared memory in the computer, what's also called the heap memory. So you don't have to worry about this value being cleared. The runtime is going to recognize that you're returning a pointer from the local stack, and everything is going to work for you just fine. And it makes a lot of things more convenient, because within the function, we can work with this as a true value, so we don't have to worry about dereferencing pointers. And then just right at the end, we can return the address of the result, and the runtime makes it all work for us. Another thing that we can do in the Go language, and this isn't done very often, but there are cases where it is valuable, is using named return values. So if I drop in this example here, notice that I've changed my return value now. I've got a set of parentheses here, and then I've got a name for the return value and a type for it. So when you do this, this is basically syntactic sugar for declaring a result variable. So this variable is going to be available in the scope of our sum function, And then that value is going to be implicitly returned. So we can work with that result variable right here within our function, and then we don't have to specify the name of the return variable down here on line 17. We just have to tell it to return. So when we run this, we see that once again we get exactly the same behavior, but the body of our sum function is actually quite a bit cleaner because we don't have to do the maintenance of instantiating this result variable. Now this is actually not done very often in the Go language, and my suspicion is because it can be a little bit confusing to read, because your return variables are declared way up here at the top of the function, and your actual return is down here at the bottom. So if you're reading this code and you're trying to figure out what this function is actually going to return, you have to come all the way back up to the function signature. So this can be a very valuable technique to use, but I would be very careful with it, because if you've got long functions, then named result parameters can actually be more confusing instead of less confusing. So you have the option there, pick whichever one makes the most sense for your application. The last thing that I want to talk about with return values is the fact that we can do multiple return values from a function. So in order to show you why this is valuable, let's take this example here. So I've created a simple divide function that takes in two parameters, a and b, that are float 64s. It's going to divide them and it's going to return that result back. So if I run this, I get 1.66666, like you might expect, and everything's fine. But what happens if I pass in a 0 here? Now when I run this, I get an unknown result. I get a positive infinity result, and I can't work with that in my application. So I'm going to probably cause some sort of a failure down the line. So in a lot of languages, the only thing we could do is throw an exception or panic the application in Go when we detect that there's this invalid value for the parameter b. So I guess we could do that. We could add some kind of logic here. If b equals 0.0, then we're going to panic, and we're going to say cannot provide 0 as second value. And that would work, but keep in mind when we talked about control flow in Go, we don't want to panic our application as a general course of action, because panicking means the application cannot continue. Now in fact, this application cannot continue if somebody provides a value of b. But it's reasonable to assume that we might pass 0 in for this b parameter occasionally. So instead of doing this, what we actually want to do is return an error back, letting the calling function know something that they asked it to do wasn't able to be done properly. So instead of doing this, we're actually going to add a second return variable. So to do that, we're going to add a paren here, and we're going to return an object of type error, and then close that parenthesis off. So we can return as many values as we want from a function, but this is a very idiomatic way of using the Go language. So we're going to return the intention of the function as the first return value, and then we're going to return an error object in case something went wrong. So in that case, what we're going to do is we're going to remove this panic, because we really don't want to be doing that, and we're going to return the first value. We're just going to zero it out because we can't do this operation, so we can't return anything meaningful. And then we're going to return an error object. Now you can generate one of those by using the error_f function, and we can say cannot divide by 0. So we're going to provide a value for that error, and then that's all we need to do here. So since we've returned out of this function in the error case, then if we get past it, we can continue as if our parameters are okay. And so in that case, we can actually do our operation. And then for the error value, we're going to pass nil because no error was present. And again, this is very idiomatic Go. We're going to return an error value if something went wrong, and then we're going to explicitly return nil if nothing went wrong. And then if you've read any amount of Go code, you've seen this quite a few times. We're going to check to see if that error, so we got our standard if error is not equal to nil, and then we're going to put our error handling logic in here. So in this case, all we're going to do is print out the error and return from our main function, so we're going to exit our application. If we don't have that, then we're going to just print out the result of our calculation. So again, this is a very common pattern in Go. Inside of your functions that can generate errors, you're going to return the expected value and then an error as the second parameter. Then you're going to have a guard that's going to check for those error conditions. You're going to return as soon as possible from your function with the error value if an error is present. And the reason for that is we're going to try and left justify our code as much as possible, so we don't end up with these pyramids of doom where we're going to have else checks and we do all of our error checking at the bottom. We're going to do our error checking at the beginning and then return out as soon as possible. So if we do get past that, then we're going to be on our happy path and we're going to return out the result of our calculation and then a nil error. Up in the calling function, we're going to have the standard test to see if error is not equal to nil. If it isn't equal to nil, then we're going to process that error because now we've got something we're going to have to deal with. And then again, we don't have an else block here. We just continue moving on we're going to make sure our error handling logic either recovers from the error or exits out of the function, and that way we can keep our main thread of execution left justified. So our main thread of execution here is we're going to call this divide function, and then we're going to print out the result. So any error handling should not force the main line of execution to be indented. So now if we run this, we see that I forgot to initialize my error parameter, so let's go ahead and add that. And this is something else I should talk about. When we're receiving multiple values out of a function call, we actually have a comma delimited list of those return values. So this D parameter is going to match up to this float64, and this ERR parameter is going to match up to this error parameter here. So now if I run, everything should work. And we see that we now get an error, cannot divide by 0. So our main function doesn't explode on us. We actually have something that we can work with. But if we put in a valid value, then we're on that other path of execution and we get the return value back out. Now, so far we've been treating functions as this special thing because we're always using this func keyword. We're declaring these at the top level of our application and we're working with them. But functions in Go are actually more powerful than that, because functions themselves can be treated as types. They can be passed around as variables, they can be passed as arguments into functions, you can get them as return values. Pretty much anything you can do with any other type, you can do with functions. So let's take a look at that a little bit. So in this example, I'm actually declaring a function on the fly, and this is called an anonymous function. Now we're going to continue to explore this over the next couple of minutes, but this is the simplest example I could come up with. So notice that I'm starting with the func keyword, I've got the parens for the parameters, I've got the opening and closing curly brace, but I don't have a function name here. So when you're doing this, this is what's called an anonymous function, and this is the basic structure of a function when you're not working with functions in this traditional scope, but instead you're working with functions as types. So inside of my function body, I'm printing out the message hello go, and then I've got, accompanying my closing curly brace, these parens here. Now these parens here are basically going to invoke this function. So this is an immediately invoked function. I'm defining it and executing it at exactly the same time. So when I run this, it actually does execute that function, and we get the value hello go printed out. If I don't have these parens, then the compiler's a little confused. It doesn't know what to do with this function. It's just defined, but it's never used anywhere, so it fails a compilation check. But if I do invoke that function immediately, then I get this behavior here. Now, why would you use an anonymous function like this? I actually have no idea why you would use an anonymous function like this. I mean, there can be situations where you can declare variables inside of here. So if I declare a message variable here and I set that equal to this string and then print that out, that can be valuable because you're actually generating an isolated scope. So this message variable is not going to be available in the main function. It's only going to be inside of this anonymous function here. Now another place that you might use this is if we've got a for loop. So if I start up a simple for loop and I'll just count up to 5 and increment by 1, see if I can do this on the fly here. And then I come in here and I actually print the value of I out. So I'll get rid of this message here and I'll print out I. You're going to get a little bit of strange behavior. If I run this, this works okay. But as we start getting into asynchronous code, things are going to start behaving a little bit oddly. So we do have access to this I variable because we're in the scope of the main function, and so inner functions can actually take advantage of variables that are in the outer scope. But the problem is, if this function is actually executing asynchronously, then this counter variable is going to keep going, and we may actually have odd behavior here. So the best practice is actually to provide a variable inside of here and actually pass that I variable. And what that's going to do is we're not going to be reading from the outer scope anymore. We're going to be passing that into the function execution. And that way, even if this is running asynchronously, we're going to print out the value correctly. Now, this works correctly in the playground the way that we have this right now because we actually aren't doing anything asynchronously. This is all synchronous execution. And so we are safe to use this outer counter, but it's not good practice to do that. Instead, it is best practice to pass in that counter variable if you need that in your inner function. That way, changes in the outer scope aren't reflected on the inner scope. Now, taking this a little bit farther, we can work with functions as variables, like I said before. So in this case, I've declared an anonymous function, and I've assigned that to this variable f, and then I can execute f by just invoking it like any other function. So if I call that, we see that we do print hello go out. So now that I've got this function defined as a variable, it's free to pass around my application. Now, you might ask yourself, what is the signature for this function? So let's go ahead and go through that. So if I get rid of the short syntax and extend this out a little bit, then I'm going to start with the var keyword. And since this is a very simple function, the type is just like this. We have the func keyword and then an open and close parenthesis. So the parameters normally go in here. I don't have any parameters here. I don't have any return types. So the type signature for this variable is simply func with 2 parens there. So if I run this, that works just fine. Now we can go a little bit more complicated, and I'll drop an example of that in just to show you how that's going to look. So in this case, I'm declaring a function signature for a divide function. That's going to take in two floats, and it's going to return a float and an error. And you see this is the syntax for that. So we pass our parameter types in here, and then we have the return types in parens as well. If you have just a single return type, then you don't need these parens. We could just put the type there like that. But we do have that error type that's coming back, so we do need to include that. And then when I initialize that variable, I'm going to set it equal to an anonymous function that takes a and b, and this is exactly the same divide function that we had before, and I can call that exactly like we had before. So when I run this, it has exactly the same behavior as the last example we did with the divide function, but now we have the divide function declared as a variable, and we're working with it exactly the same way as when we declared it as a function. Now the difference between this and when we had the divide function declared globally is if I try and call it up here, and run the application, notice that I get an error, because in this case, the function divide hasn't been declared yet because it's declared as a variable, and so I can't work with it yet. So that's just something to be aware of. If you're going to be working with functions as variables like this, make sure that they're defined before you actually try and execute them. Okay, the last thing that I want to talk about with functions today is working with what are called methods, and there's a couple things to talk about with those. So let me just drop in an example that shows that, and we can walk through this and then see what it's going to do. So in this example, I've got a struct called greeter. That greeter struct has two fields, greeting and name, and then I've got this method on it, and we'll come back to this in a second. So in my main function, I'm declaring a greeter struct, and then I'm calling this function, preceding it with the struct that I have here. And this is how we're going to do method invocation. So we call the method just like we were accessing a field, except for we have the parens here where we can pass some arguments in. Now my method declaration down here looks a lot like a function, except for it's got this odd bit right here. And this is what makes this function into a method. So a method is basically just a function that's executing in a known context. And a known context in Go is any type. Now it's very common that we can use structs, but you can use any type. So we can make a type for an integer. So maybe we have a type for an integer called counter, and then we can add methods onto that counter type and work with those. So when we declare that method, we're actually going to get access to that type right here in this part. So what's going to happen when we call the greet method is the greet method is going to get a copy of the greeter object, and that's going to be given the name G in the context of this method. So then when we print out, we can access the fields on that greeter object, so we can print out the greeting and the name. So when we go ahead and run this, we see that we get hello go printed out, and that's the basics of a method. So methods are basically the same as functions. They just have this little bit of syntactic sugar that's providing a context that that function is executing in. And when we do that, we call that a method. Now, when we use this syntax right here, notice that we're specifying greeter as a value type. We don't have a pointer here. So this is what's called a value receiver. The received object in this greet method is the value greeter. So what that means is just like any other time that we're working with values, we are getting a copy of the struct. We're not actually going to get the struct itself. So if I change the value of the name field here, and then I print the name field out up here, so I say the new name is, and then I print the name field out, then it's no big surprise that even though I assigned an empty string to the name field here, up here in the main function, it didn't have any effect. Because down here in this method, we're operating on the copy of the greeter object. We're not operating on the greeter object itself. So again, that's very valuable if you want your methods to be able to access the data of their parent type without being able to manipulate it. Just keep in mind there is a cost with that. So if this greeter object was a very large struct, then we would be creating a copy of that struct every time we invoke this method. Now, as you might expect, there's another option that we have here, and that is to pass in what's called a pointer receiver. So if we make this a pointer and run the application again, now we're actually able to manipulate that underlying data. So we're going to print out hello ghost, so the method operates in exactly the same way, and we don't have to change the format here because we do have that implicit dereferencing of pointers that's working for us. But now when I change the value of the name field and print the name field out up here, we do in fact see that we've been able to reassign the value of that field. Okay, so that covers the working with functions in the Go language. Let's go into a summary and review what we've talked about. In this video, we talked about functions and how to use them in the Go language. And we started out by talking about the basic syntax of a function. And we saw that this is about as simple of a function as we can get. So we start with the func keyword. We have a name for that function. And again, if that first letter is uppercase, then that function is going to be published and allowed to be executed from outside of the package. But with a lowercase first letter, it's going to be kept internal to the package. Then we follow with a matched set of parentheses, and then we have an open and closed curly brace. Now the open curly brace has to be on the same line as the func keyword, and the closed curly brace has to be on its own line after the final statement of the function. Then we moved on to talk about parameters, and parameters allow us to pass data into the function to influence how that function executes, basically providing some variables for the function that are passed in from the outside. So we talked about how parameters are passed in as a comma delimited list of the name of the parameter and the type of the parameter. So we see here we're passing into the foo function two parameters, the bar parameter that's of type string and the baz parameter that's of type integer. Parameters of the same type can be comma delimited and the type can be listed at the end there. So in this case we're passing in bar and baz as parameters, and both of those are going to be of type integer. When pointers are passed in, the function can change the value in the caller. So by default we're going to be passing in the values themselves, and so the Go runtime is going to be copying that data and passing it into the function, so any changes that are made inside of the function aren't going to be reflected in the caller scope. However, if you pass in a pointer, then you are going to be able to manipulate the value inside of your function, and that will have an effect in the calling scope. So the only exception to this rule is when you're working with slices and maps. Since they work with internal pointers, any changes inside of the function to the underlying data is always going to be reflected inside of the calling scope. We also talked about how you can use variadic parameters to send a list of the same types in. So it must be the last parameter in the parameter list. It's received inside of the function as a slice, and you see an example of the syntax right here. So we've got the function foo, it has one parameter bar that's of type string, and then a parameter baz that's a variadic parameter of integers. So inside of this foo function, we're going to have a slice called baz, and that's going to contain all of the integers that have been passed in. Once your function finishes doing its work, a lot of times we want it to return a value back out, and in order to get that information back out, we're going to use return values. So if you have a single return value, all you need to do is list the type. So in this case, our foo function needs to return an integer. We can also specify multiple return values. So if we're going to do that, we need to put parens around the types that we're going to be returning. So in this example, we're going to be returning an integer and an error. And this is a very common pattern that you're going to see in Go applications, where we're going to have our functions return the intended value and then an error value that's going to let the caller know if anything went wrong. That way, the function itself doesn't have to determine whether the application needs to panic or execution can't continue. It just knows it wasn't able to do what it was asked to do, and then it can delegate what that error means to the application to the calling function. You can also use named return values. So when you do that, instead of just providing the types in the return list, you're going to provide the name of that return value. So when you do that, the runtime is going to initialize that value for you to the 0 value for that variable. And when you use the return keyword, all you need to do is enter return on its own. Go is going to find the current value of those return variables, and that's what's going to be returned out of your function. Another special behavior of Go is you can actually return the addresses of local variables as return values, and those are going to be treated properly. So when you do that, those variables are automatically promoted from local memory or stack memory up into shared memory or heap memory, so you don't have to worry about those values being cleared out as the function's stack memory is reclaimed. We then started talking about anonymous functions, and we talked about a couple of different uses for those. So we have this immediately invoked function, which really isn't used too often in the Go language, but it's as simple of an anonymous function as I could get. The only potential advantage that you have here is that you can create an inner scope, so local variables that are created inside of this anonymous function aren't going to be available outside, but I haven't seen that very often. It's not going to be very often that you're going to need to use this kind of a function. Then we also talked about how we can take that anonymous function and actually assign that to a variable. So in this example, we've got the variable a assigned to the value of that function. And then we can invoke the a function just like any other function. The only difference between this and the normal declaration of a function is that the a function can only be invoked after it's been declared. So when you declare a function using the traditional syntax, it's actually declared at the time that the package is initialized, and so it's always available to you. When you're using this syntax, you have to make sure that a is initialized before you can call it. Extending on that discussion about the ability to assign functions to variables, functions are types just like any other type in the Go language. Anytime you can use a primitive or a slice or an array or a map, you can use a function. So you can assign them to variables, you can use them as arguments, they can even be return values from functions. Then we also talked about how, since a function is a type, we have to have the ability to create a type signature. So if you're declaring anonymous functions, it's often most convenient just to use that : equal syntax and declare your anonymous function, and the type is going to be inferred. However, if you're using a function as a parameter to another function, or as a return value from a function, then you're going to need to specify that type signature. So we see an example here. In this case, we've got the definition of a function f, and that function is going to take 3 parameters, 2 strings and an integer, and then it's going to return an integer and an array type. So it's basically the same as when you're declaring a function normally. The only difference is we don't have the names for those variables, because those names will be provided when we actually implement the function. We just need to know the types that are coming in and the types that are coming out at this point. The last thing we talked about were methods, and how a method is a special type of function that executes in the context of a type. Now, a type doesn't have to be a struct, although that definitely is a very common use case for methods. You can actually attach a method to any custom type. So you can create a type of an integer, and then you can add methods onto that integer. When we create a method, we're going to use a modified version of the basic function syntax. So before the name of the function and after the func keyword, we're going to provide another set of parens. We're going to provide a local name for the type that's going to receive that method, and then we're going to follow that with that method type. Now that variable is what's called the receiver for the method. So in this case, our G variable is what's called a value receiver, which means we're going to get a copy of that greeter object, and that's going to be passed into the greet method. However, we can also use what are called pointer receivers. So by adding an asterisk in front of that greeter type, the method is going to change. So instead of passing a copy of the greeter, we're going to get a pointer to the greeter object in there, and then any manipulations we make to the greeter object in the greet method are going to be reflected throughout your application. Now that's very powerful if you need the method to be able to manipulate the state of the object. It's also much more efficient if you're dealing with large structures, because instead of copying the entire structure, it only has to copy a pointer, and that's normally a much more efficient operation. Okay, so hopefully that helps you understand how functions work in the Go language. If you have any questions or comments, feel free to leave those down below. I'll try and get back to you as soon as possible, and we'll come at you soon with another video introducing you to the Go language.